Welcome students to this video. The purpose of this video is to cover material that we would have discussed in class on Tuesday, February the 12th, but did not because, well, school closed due to a snowstorm. Let's start with a discussion of trends in the periodic table. The periodic table is an interesting presentation of the elements, very organized and highly orderly. The properties of elements will vary systematically if we go across rows or down columns. For example, the boiling point of elements increases going down a column of the periodic table. The density of elements increases going down a column. We'll examine the trends in three important properties of elements: atom size, the ionization energy, and electron affinity. First, let's talk about the size of an atom. The size of an atom of an element is basically determined by the average distance between the outermost electron and the nucleus. This distance, the radius of an atom, we call it, of course, atomic radius, can be measured experimentally. Atomic radius depends on two factors. First, it depends on the main energy level containing the outermost electron. Secondly, it depends on the nuclear charge felt by the outermost electron. We refer to this as effective nuclear charge. Now, the outer main energy level. Other things being equal, the higher the main energy level that contains the outermost electron, the further the electron is from the nucleus. That is, the larger the radius of the atom. In the example here, we compare the size of two atoms, a helium atom with a hydrogen atom. In the helium atom, the outermost electron is in the second main level. It's relatively far from the nucleus, compared to a hydrogen atom in which the outermost electron is in the first main level. Closer to the nucleus, therefore the hydrogen is a smaller atom. With respect to effective nuclear charge, we mentioned that we've talked about effective nuclear charge in a previous class, but we're going to discuss it now. The greater the nuclear charge felt by the outermost electron, the stronger the attraction on the electron, pulling the electron closer to the nucleus, a factor that makes the radius of the atom smaller. Now, when we previously talked about effective nuclear charge, we introduced Slater's rules. These are a set of rules which will give you a fairly accurate computation of the effective nuclear charge. I am not going to strictly apply these rules. Rather, we're going to do a simplified application of these rules. Let's look at the lithium atom. It has one electron in the outer main level and two electrons in an inner main level. There are three protons in the nucleus. The one outermost electron really no longer senses a +3 charge on the nucleus. That's, of course, the true charge on the nucleus, because the two interlying electrons basically neutralize or cancel the charge of two protons in the nucleus. That is, the inner electrons, the inner two electrons, act as an insulator, reducing the positive charge that the outer electron actually feels from the nucleus. The outermost electron senses, therefore, only a +1 charge from the nucleus. The effective nuclear charge is +1. Now, there's a general formula that we use to discuss the effective nuclear charge. Z star is the effective nuclear charge. This equals the actual nuclear charge minus a quantity S. S is the so-called screening constant, and it basically measures the number of electrons that lie between the outermost electron and the nucleus. For lithium, the effective nuclear charge felt by the outer 2s electron is the actual nuclear charge plus 3 minus the number of interlying electrons that screen out the charge, which would be 2 in number. 3 minus 2 equals effective nuclear charge of plus 1. I hope that's clear. When an atom's outermost electron is in a higher main energy level, the atom tends to be larger. When the effective nuclear charge sensed by the outermost electron is large, the atom tends to be smaller. All right. Variation in atomic radius. This is with respect to the periodic table. The atomic radius we find increases going down a column of the periodic table. It decreases going from left to right across a row of the periodic table. Well, this needs some explanation. If we go down a column, going down a column of the periodic table, we find that the atomic radius increases. The atom gets larger. And the reason is because the outermost electron is found in an increasingly higher main energy level as one goes down a column. And thus the outermost electron is farther from the nucleus. On the other hand, the effective nuclear charge felt by an outermost electron is basically the same for all elements in a given column, and is not a factor in determining atomic radius. Let's illustrate with an example. A potassium atom has a larger atomic radius than a sodium atom. Potassium lies right below sodium. Both elements are in column 1. Here are the values of the atomic radii of potassium and sodium. Here's the rationale. The outermost electron of potassium lies in a higher main level, n equals 4, than the sodium, which the electron lies in an n equals 3 outer level. But for potassium and sodium atoms, the effective nuclear charge felt by the outermost electron is the same, plus 1. So for potassium, the effective nuclear charge is the nuclear charge 19 minus the number of interlying electrons 18 plus 1. For sodium, the effective nuclear charge is the true nuclear charge 11 minus the number of interlying electrons 10, which gives us the same plus 1. Therefore, potassium would have a larger atomic radius. Its outer electron lies further from the nucleus. The effective nuclear charge for both is the same for both potassium and sodium. The diagram shows all of this. Sodium is larger because its outer electron lies in basically layer number 1, 2, 3, 4, whereas sodium, the outer electron lies in layer number 3. Layer 4 is larger, lies further out from the nucleus. The effective nuclear charge, the calculation for sodium potassium, is basically the same, plus 1. So that's not a factor in determining size. But the fact that potassium's outermost electron lies in the higher main level in a larger outer layer makes it a larger atom, one with a larger atomic radius. Let's now look at the variation in atom size going across the row. Going from left to right across a row of the periodic table, atomic radius decreases, we find. Now this is kind of counterintuitive. If you're going from left to right, you're adding more things to the atom. If you add more things, you would seem that it ought to get bigger. More things make something bigger. Well, what's going on here is that the effective nuclear charge felt by the outermost electron increases, because when you go across a row, you're successively increasing by increasing the nuclear charge by +1 because you're adding an additional proton to the nucleus. The additional electrons that you add, when you move across the row, you add also an additional electron. Each of those electrons basically goes in the same outermost level, outermost layer. Therefore, the outer electrons are pulled closer to the nucleus because of the greater effective nuclear charge, and the atomic radius decreases. The electrons in the same main level don't screen the other electrons very well. Here's an example going across the row containing sodium and magnesium. Magnesium is right next to sodium. Experimentally, we find that the magnesium atom is a smaller atomic radius than the sodium. There's the values: magnesium 0.16 nanometers and sodium 0.186. Magnesium is smaller. All right, the effective nuclear charge that's felt by the outermost electron of magnesium is greater than that of sodium. And here's the calculation effective nuclear charge. For magnesium, the actual nuclear charge 12. The number of interlying electrons is 10, so it's +2. And you can see that down here. So here's the sodium's outermost electron. Number of interlying electrons is 8 + 2 is 10. So actually, I'm sorry, this is sodium. Well, we'll go ahead and do sodium. Sodium's calculation shown up here. So the actual nuclear charge for sodium is +11. The number of interlying electrons is 10. So 11 minus 10 is +1. And the calculation right there. Magnesium, which I first mentioned right here, let's go look in the details of that. One of the outermost electrons of magnesium, there are 2, is here. The number of interlying electrons is 8 + 2, which is 10. So actually this calculation has an error in it. So it's the actual nuclear charge +12 minus the number of interlying electrons. 8 + 2 is 10. That gives you +2. All right, so the effective nuclear charge felt by an outermost electron in magnesium is +2. Effective nuclear charge in sodium is +1. All right, so the outer electron magnesium feels a greater pull. The greater pull pulls the outer electrons closer to the nucleus. The atom shrinks in its size and gets smaller. That's why magnesium then is smaller than sodium. It has a smaller atomic radius. The next property we're going to look at is ionization energy. Well, what do we mean by ionization energy with respect to an element? If you pump enough energy into an atom of an element, you can remove an electron. The electron that will be first lost is the one that's in the highest energy level, the one that's easiest to remove. The energy required to remove the outermost electron is in fact called ionization energy. We abbreviate that IE. Take, for example, a sodium atom. If you pump in enough energy, you can remove the outermost electron of sodium, producing a +1 ion, shown by the equation here. Now, the measured energy required to do that is 496 kilojoules per mole. Now, you could, in principle, take that sodium +1 ion, pump energy into that, and remove a second electron, producing a +2 ion. We're going to focus now on the energy required to remove one electron from the neutral atom to form the +1 ion. That's called the first ionization energy. If one measured the energy required to remove the second electron to form a +2 ion, that's called the second ionization energy. So our focus right now is on trends observed for the first ionization energy. Um, hopefully it's kind of obvious. When you remove an electron from a neutral atom, it's going to be the one that's easiest to remove. That's the outermost electron that will be removed. And that's because the outermost electron is less strongly held by the nucleus. It lies in a higher energy level. It makes it easiest to remove. All right. There are systematic variations in the first ionization energy of the elements we discover with respect to going down a column or going across a row. If you go down a column of the periodic table, we find that the first ionization energy decreases. If you move from left to right across the row of the periodic table, we find that first ionization energy decreases. The best way to understand that is to think about what we just discussed with respect to atom size. The ionization energy is related to the strength of the attraction of the outermost electron to the nucleus. The stronger the attraction, the higher the ionization energy, the harder it is to remove the electron. If you go down a column, remember that the size of the atom increases while the effective nuclear charge felt by the outermost electron really doesn't change. The outermost electron is increasingly farther from the nucleus, and thus the outermost electron is less strongly attracted to the nucleus, that is when you're going down a column, and so consequently it's easier to remove the outermost electron going down the column. Ionization energy decreases. Example, sodium and potassium. Potassium lies right below sodium. Here the observed ionization energy for sodium, it's 496. For potassium, it's less. It's 419 kilojoules per mole. If we go across the row of the periodic table, remember we learned before that if you go from left to right across the row, the size of an atom decreases, and that's because the effective nuclear charge felt by the outermost electron increases. You're adding an additional proton every time you go from one element to the next, from left to right. Now, because the size of the atom is smaller, going from left to right, with a greater nuclear charge, the outermost electron is going to be more strongly attracted to the nucleus. It's held more strongly and thus harder to remove. Therefore, ionization energy is going to increase going from left to right. Example, as we saw before, moving from sodium to magnesium, they lie in the same row, first sodium and then comes magnesium. Here are the observed ionization energies. It's 496 for sodium, 738 for magnesium, larger. There's also a trend in the radius of ions, the ionic radius. The radii of cations and anions from the main group elements follow actually the same variation as do the radii of neutral atoms. Basically, the same factors come into play. The main level containing outermost electrons, effective nuclear charge, and so forth. Thus, the ionic radii of ions they increase going down a column, and they decrease going from left to right across a row of the periodic table. Now we come to an interesting property, which you may or may not have a good sense of. This should be covered in general chemistry. It's called electron affinity. And let's define it. Now, ionization is the removal of the outermost electron. Suppose you take a neutral atom and you add an electron to it. It's going to make an anion. The energy change that occurs when you add an electron to an atom to make an anion is related to what chemists call electron affinity. Now, let's be careful as we define this, and a lot of textbooks kind of gloss over this. The symbol for electron affinity is EA, capital E, capital A. Technically, EA is defined to be the negative of the energy change resulting when an atom gains one electron. It is to say, say we have an atom A and we add an electron, producing an anion. The electron affinity is the negative of the energy for that. And if you think about technically what it is this equation written in reverse. It's the ionization of the -1 anion to produce the neutral atom. That is what is really electron affinity, that energy change. Now, defined in that way, we find that most elements exhibit positive electron affinity values, that is greater than 0. The process of an atom, of an element gaining 1 electron is exergonic, means giving up energy. Fluorine, for example, it's a highly exergonic process, adding 1 electron. Adding 1 electron to fluorine makes F-1. The energy change for this is -328. And now if we take the negative of this, which that's how we define electron affinity, minus a -328 gives us plus 328 kilojoules per mole. Now, there is a regular trend we observe for electron affinity. Essentially, the EA values for elements in the periodic table follow the same trend as ionization energy. Well, what physical meaning can we put to electron affinity? It has a useful meaning. You can basically think of it as the intrinsic attraction that an atom of an element has for an electron. If the EA is large, the element has a strong affinity, a strong attraction for an electron. If the EA is low, the element has only a weak attraction for an electron. If you go down a column with respect to EA values decrease going down the column periodic table. Because an atom gets bigger going down the column, the outer shell getting the added electron is further from the nucleus, and thus the attraction between the atom and the added electron is less. If you go across the row, the EA values increase from left to right across the row of the periodic table because the atomic radius, of course, we learned decreases, effective nuclear charge increasing, going from left to right. Well, if in doing that, the electron's more strongly attracted to an atom, thus giving increase in EA values. This chart here shows, in fact, that the trends observed for ionization energy and electron affinity really follow the same pattern. Now, let's talk about electronegativity. Electronegativity is an important quantity that it's discussed in organic chemistry. I think you all have a good sense, understanding of what that is. Electronegativity is represented by the symbol chi, small case Greek letter. It's defined as the intrinsic attraction exerted by an atom for its bonding electrons. So it makes reference to an atom forming a bond to another atom, as in a molecule. A number of chemists have introduced procedures for getting a numerical value for electronegativity. It's a quantity that is not measured directly, but it's computed from observed physical properties. First to really do this is Millikan. Millikan took as electronegativity the average of the delta H for electron affinity and the delta H for ionization of an element. And this is really based on the idea that the attraction of an atom for its bonding electrons, it's really a balance between the element's tendency to gain an additional electron and its compulsion to hold on to the outer electron it already possesses. All right, Linus Pauling, I hope you all know who he is. He's famous. He actually won 2 Nobel Prizes in chemistry and also in peace. He demonstrated against nuclear weapon testing back in the late 50s. Electronegativity, in Pauling's view, it was based on this notion that the degree of ionic character of a covalent bond between two elements reflects a difference in electronegativity between the bonded elements. So the bigger the difference in electronegativity for two atoms bonded, the larger the ionic character. Consider a diatomic molecule A bonded to B. What Pauling did in his approach is this. He computed the average of the bond energies for AA and BB. So we have two different elements bonded covalently. He computed the average bond energy, or rather he took the observed bond energy for observed for AA and for BB, and he took the average of those. Now actually, when I say the average, he didn't do the arithmetic average. He actually calculated the geometric mean for that. Well, if you don't remember what that is, I'm going to explain it in just a bit. All right. He took that average and compared that to the actual observed bond energy for AB. The idea is this: the larger the difference between these values, the greater the difference in electronegativity between the bonded elements. This is going to be much clearer with a specific example. Let's take the diatomic molecule HF, H covalently bonded F. The observed bond energy is 566 kilojoules per mole. Now that's, of course, the energy required to completely break that HF bond. The observed bond energies for bonds between like atoms, we have HH bond and FF bond. Well, here are the values here: 436 for HH and 158 for FF. Okay, what he did is he computed the geometric average, the geometric mean of these two bond energies. Now, geometric mean, what you do is you take the square root of the product of the two values, the square root of the product. The arithmetic average would be to take the sum of two values and divide by 2. Here we're taking the product of the two values and taking the square root of it. Anyway, if you take the geometric mean of these two values, you come up with 262 kilojoules per mole. The key now is to compare this geometric mean with the actual bond energy. The actual bond energy is 566. The geometric mean is 262, so the difference is 304. The idea is the larger the difference here, the greater the difference in electronegativity between those bonded atoms. A delta, of course, is a symbol for difference. Now, to get a consistent set of electronegativity values for all of the elements, Pauling came up with an empirical equation shown here. The difference in the electronegativity of two elements equals a constant, the parameter 0.102, times this delta difference to the 1/2 power, the square root of that. I call that equation 1. Now what Pauling did is he developed a scale of electronegativity values. He arbitrarily assigned a numerical value to, fluorine. Fluorine has the highest electronegativity, so he arbitrarily assigned a value 4 for that. Now if you go back to his little equation here, if you substitute 4 for the electronegativity of fluorine, and you then calculate the electronegativity for hydrogen. The delta value here we previously calculated to be 304. You plug that in here, take the square root, multiply by that constant 0.102. This is subtracted from 4, and he calculates that the electronegativity of hydrogen then is 2.22. So proceeding in this way, where we now have we have an electronegativity value for one element, and we don't know the other. We have the a bond formed between the two, the observed bond energy for that, and so forth. Using that equation, Pauling can generate electronegativity value for, well, proceeding that way for basically all the elements. Now here's another approach for calculating electronegativity due to a couple of workers, Allred and Rocho. They calculated electronegativity values for elements based on Coulomb's law. Basically a very simple, intuitive idea. Now, Coulomb's law, of course, states that the attractive force between two charges is the product of the charges divided by the square of the distance between them. Now, what it comes down to is this. It's a question of the outermost electron, how far it is from the nucleus, and what the effective nuclear charge is felt by that outermost electron. So the key equation of theirs is shown here. The key variables are the effective nuclear charge of the outermost electron, Z star, and the distance between that electron and the nucleus. That's given here r squared, the square of the distance between basically the electron and the nucleus. Experimentally, that comes from observed the covalent radii for atoms that are involved in bonding. There's some constants in this Allred-Rocho equation, 0.359, 0.744. Those are chosen to make their electronegativity values consistent with the Pauling scale electronegativity values. It's appropriate now to take a look at the systematic variation that we see in electronegativity values in the periodic table. Generally, electronegativity values increase going across the row of the periodic table, and they increase moving up a column of the periodic table. So increase going from left to right across the row, increase going from bottom to top up a column of the periodic table. Here's a little way to help remember that. Remember that fluorine has the highest electronegativity. Well, fluorine F is in the upper right-hand corner of the periodic table. The fact that it's situated there means that everything to the left is a lower value, so obviously you're going to have to increase going from left to right. If fluorine is the highest, everything below it is lower, so you're obviously going to have to increase in electronegativity going from bottom to top, proceeding up a column of the periodic table. And now I want to talk about structure and bonding in molecules, and actually this gets in now to the next chapter of our textbook. There are two operational models of bonding today. They're based on different assumptions, and I guess you could say there's a competition between the advocates of both schools of thought. One's called valence bond theory, and the other is molecular orbital theory. Molecular orbital model, the atoms of a molecule are viewed as held together by sets of large balloon-like orbitals that envelop the entire molecule, or at least significant portions of it. These orbitals are called molecular orbitals. Now we're going to talk about molecular orbitals, but that'll be down the road a bit. What I want to go into right now is the valence bond model. In this model, bonds are assumed to rise from the overlap of electron-containing outer orbitals of adjacent atoms. So we have atoms A and B, and their outermost electrons, the orbitals containing those outermost electrons. Well, when they get close enough together, those outer orbitals basically overlap. The total of the two electrons will reside largely in that overlapping region, and thus we form a bond. That's called a shared pair shared electron pair bond, or technically called a covalent bond. Now the outer orbitals involved here comprise what is called the valence shell of the element. For main group elements of the periodic table, the valence shell consists of the outermost s and p orbitals. The electrons in the valence shell are called valence electrons. Now the basic driving force for atoms bonding together in a molecule is to acquire a full valence shell. Every atom, its goal is to acquire a full valence shell and achieve a stable inert gas configuration. Once the molecule is completed, valence electrons will, there's two forms that you'll find. They're either going to exist as shared electron pairs or as unshared lone electron pairs on an atom. Now in general chemistry, you learn a set of steps that will, if you follow the steps, you'll be able to draw a structural formula for a molecule. It's also called the Lewis structure. When I go over the rules briefly, what you want to do is first count the total number of valence electrons in the molecule. Next, you want to locate the atom that's in the center. That's called the central atom. And there's a couple of ways to do this. Once you've located the central atom, the idea is to bond all other atoms to the central atom with single covalent bonds. You would then want, in your skeletal structure, count the number of electrons that you have, subtract from the total number of valence electrons. That tells you how many electrons you have to add to finish the molecule. Well, those added electrons are going to be added as unshared electron pairs. You add them first to the outer atoms, work your way towards the central atom. The central atom, you add the lone pairs last. Now, the whole idea is that you will get a structure, a correct structure of the molecule, when all of the atoms have acquired a full valence shell and no other obvious rules are violated. Now, some cases, well, if you have, for example, elements in row 3 or below, those central atoms can actually have more than 8 valence electrons. It can be 10 or 12, and such atom is said to have an expanded octet. You will discover that when you actually sit down and start putting the atoms together, drawing the structure that the central atom will have more than 8, and you just add those extra pairs in. Here's some examples of Lewis structures that can be constructed by applying those previously described steps. All right, they're grouped as follows. The first group are molecules that contain only single covalent bonds. This is CH4 methane. Here's the structural formula for water. Note that the central oxygen has 2 bonds and 2 unshared electron pairs. This is the completed structural formula for ammonia. Nitrogen has 3 bonds and 1 unshared electron pair. These 3 are molecules that have, well, they all have a double bond. Refer to those as unsaturated molecules. This is acetone. It's got a carbon-oxygen double bond. This is a nitrate ion, NO3 minus 1 ion. And this is a sulfur dioxide molecule. All of those have at least 1 double bond. Down here are examples of molecules in which the central atom is row 3 or below. Remember, if it's in row 3 or below, they can have more than 8 valence electrons. This is phosphorus pentachloride. It's got 5 bonds, or a total of 10 electrons in its valence shell. Boron trifluoride, if you count up all the electrons that we're seeing in the around the central atom. It's got three bonds, 3 shared pairs, and 2 lone pairs. That's a total of 1, 2, 3, 4, 5, 2 times 5, 10 electrons in its shell. Here is xenon difluoride. The total electrons 1, 2, 3, counting pairs, 1, 2, 3, 4, 5, also 10, total of 10 electrons in its valence shell. All right. Now, when you get into molecules, there's a little complication that's been discovered. Largely, this is the application of the valence bond theory. It turns out that molecules are not able to construct themselves by using just simple, the intact atomic orbitals that they come with. The outer orbitals are going to have to meld together and reshape themselves, make new and different orbitals that are going to allow it to bond to the atoms and make the molecule. This just reviews the idea of a covalent bond formation. We've seen this before in the valence bond model. 2 atoms come together, electrons in the valence shell, they're out, the outermost orbitals containing electrons get close enough together that they overlap. The electron pair resides in the overlapping region, and we form a covalent bond. Well, let's consider a triatomic molecule. This is beryllium dihydride. The 3D formula for beryllium dihydride is shown here. It's a linear molecule. Well, how does beryllium form the bonds to the hydrogens and get the correct geometry, the bond angle being 180 degrees? Beryllium has to use orbitals, in fact, which will reach out to each of the hydrogens shown here. Those orbitals have to be in its valence shell. They have to be collinear. They have to both be alike in size and shape. And each has to have 1 electron, so that linking with each hydrogen atom gives you a total of 2 shared electrons, the 2 bonds. Well, if beryllium started out just as the native nascent beryllium atom, there's 2 electrons in its valence shell, and those lie in the 2s orbital. If you look at the orbitals here, the s and the 3p, those orbitals aren't arranged, lined up like we really want them to be, to make bonds to the 2 hydrogens and achieve a collinear molecule. So the beryllium has to do some fancy footwork here. What it's going to do, well, is this. It's going to take its outer orbitals, blend them together, and make 2 new orbitals that are going to allow it to make the bonds to the hydrogens. This process is found to be very general for atoms of elements in general when they bond to other atoms, making molecules. The process is called orbital hybridization. It's taking the outermost orbitals, combining them to make new orbitals that have different size, shape, and orientation that allow it to bond to atoms in the molecule it's going to make. Let's look in detail about how beryllium does that. In order to form a bond, in order for beryllium to bond to 2 hydrogens, it's going to need to make 2 orbitals. Those orbitals are going to rise by combining atomic orbitals. What will do it for beryllium is to take, in its valence shell, take its s orbital and combine it with one of the p orbitals. Now when it does that, it will make two brand new orbitals. They're called hybrid orbitals. And here they're shown here. Each orbital, well, looking at an individual, each orbital has a larger head lobe and a smaller tail lobe. These hybrid orbitals are named according to the number of atomic orbitals that combine. Since we here combine one s and one p, we call these created hybrid orbitals sp hybrid orbitals. So, all right. So let's take beryllium and follow as it's going to make its hybrid orbitals. Here's the beryllium starting out. 2 electrons in the valence shell. The configuration is 2s2. All right, orbital hybridization occurs. It's going to take the s and one of the 3p orbitals, blend them, meld them together. Boom, there it is. This is one of the sp hybrid orbitals, and here's the second one. There's a total of 2 valence electrons. One valence electron resides in one of the newly created hybrid orbitals and the other in the other one. And there it is. It's all set up. Perfect for now forming bonds, respectively, to the 2 hydrogen atoms. These newly created hybrid orbitals lie in a line. They're 180 degrees apart. Exactly what you want. So the 2 hydrogens that come in and form bonds will give you beryllium dihydride with the desired linear geometry, 180 degree bond angle. Oh, by the way, there's a technical term we use, you might remember from organic chemistry. When the shared electron pair of a bond lies right on the bond axis, that's called a sigma bond. So beryllium hydride has 2 sigma bonds. All right, summarizing, the beryllium atom of BeH2 makes and uses 2 sp hybrid orbitals to form bonds with the hydrogen atoms. And we say, the language is that the beryllium is said to be sp hybridized. There are various combinations of outer atomic orbitals that take place, producing different types of hybrid orbitals for different central atoms and different molecules. Here are some basic rules that the atoms follow. First, the total number of atomic orbitals which combine always equal the total number of hybrid orbitals that are produced. Think about that now. The total number of atomic orbitals that combine always equal the total number of hybrid orbitals. Before, we needed to make 2 hybrid orbitals, and indeed we combined 2 atomic orbitals. We combined an s and a p to make 2 new hybrid orbitals called sp hybrid orbitals. Second rule, this is important. There's a 1-to-1 correspondence between the number of outer sets of electrons in an atom and the number of hybrid orbitals used by that atom. And let's see if we can see some examples of that. What you basically do is when you have your completed molecule, you know the structural formula, you look, for example, at the central atom, and you count up the total number of sets of electrons. And the way that I define sets is important. A set of electron includes lone electron pairs and bonds. And I say bonds, that it's irrespective of whether it's a single, double, or triple. A given bond, whether it's single, double, or triple, counts as one set. So you count up the total number of sets of electrons. That number is important because that's going to equal the number of hybrid orbitals that are going to be used by that atom. And of course that's also equals the number of atomic orbitals that combine. Rule number 3, a hybrid orbital can be used not only to make bonds with other atoms, it can also hold an unshared alone electron pair. And let's see, I'm trying to find some examples to use here. Yeah, okay, let's with these molecules, I want us to understand how we count the number of sets of electrons. So if you take the first, that's methane. There's 4 bonds, 1, 2, 3, 4, 4 sets of electrons. Here, water molecule, looking at the central atom, what's the total number of sets of electrons? Well, there are 2 bonds, 2 lone pairs. That's 1, 2, 3, 4. For ammonia, the total number of sets of electrons, 3 bonds, 1, 2, 3, 1 lone pair. That's a total of 4 sets of electrons. All right. In acetone here, what's the total number of sets of electrons on the carbon? There's no lone pairs on the carbon. We have 2 single bonds and 1 double bond, a total of 3 bonds. That's 3 sets of electrons. 1, 2, 3. Some students are confused by that. They tend to want to count a double bond as 2 sets. No, the double bond includes 2 shared pairs in a bundle. They're in a single bundle, therefore 1 set. This has 3 sets of electrons. You could say 3 arms reaching out from the central carbon. Total number of sets of electrons is 3. And let's see. Well, this one, it has 2 single bonds, 1 double bond. Total number of sets of electrons is 3. Over here on this, what's the total number of sets of electrons on the sulfur? All right, let's count. 1 lone pair, a single bond, and a double bond. The double bond counts as 1 set, single bond counts as 1 set, and the lone pair is 1 set. So it's 1, 2, 3. 3 sets of electrons. All right, how many sets of electrons on the bromine here? 1, 2, 3, 3 bonds and 2 lone pairs, 4, 5. 1, 2, 3, 4, 5. Now let's go back to here. Let's see how we actually can make use of those rules. This had 3 sets of electrons. Remember, one of the important rules is that the number of sets of electrons equals the number of hybrid orbitals. So if there are 3 sets of electrons, the carbon's going to be using 3 hybrid orbitals. If it's going to make 3 hybrid orbitals, the number of atomic orbitals used to make them would also be 3. All right, now this little chart is very useful. It shows how with doing the right counting and applying the rules, we can determine the type of hybrid orbitals that are going to be used by an atom in a molecule. Step 1 is to count the total number of sets of electrons, which I hope I've explained well. This chart, there's these possibilities. You could have a total number of sets of electrons of 2, 3, 4, 5, or 6. Remember the equality. The total number of sets of electrons equals the number of hybrid orbitals that are going to be used. So when it's 2, the hybrid orbitals is 2. When it's 3, it's 3. When it's 4, it's 4, and so forth. Now, the number of hybrid orbitals, when you get that number, the next step is important. All right, for any atom of an element, when it's going to make hybrid orbitals, it always starts with its lowest energy orbital, which is an s orbital. There's 1 s orbital always. So if the total number of hybrid orbitals is 2, there's going to be a total of 2 atomic orbitals, and it's always going to be 1s. It's 1s, and it asks itself, well, if I got to combine 2 atomic orbitals, what's going to be the second one? Well, it reaches into the p region and grabs 1 p orbital. So to get a total of 2 hybrid orbitals, it's going to require 2 atomic orbitals. What are they? Well, 1s and 1p. If the total number of sets of electrons is 3, the number of hybrid orbitals is 3. What would be the what would be the atomic orbitals that the element would combine to make those hybrid orbitals? Well, it always starts with 1s. It's got to get a total of 3. We ask, well, how many p orbitals are going to be required to make a total of 3? Obviously would be 2. Now, in this case, then we deduce that to get 3 hybrid orbitals, it's going to get that by combining 1s and 2 p orbitals. The name applied to those hybrid orbitals is sp2, and there's a mistake right there. There should be a 2, not sp3. All right, that should be a 2. All right, let's look at a case of where the total number of sets of electrons is 4. Number of hybrid orbitals is the same, 4. What are the atomic orbitals? Well, it has to be 4 atomic orbitals. It always starts with 1s. What number of p orbitals would give a total of 4 would be 3. And so the label, the tag that we give to those is, and this is correct, sp3. All right, now, remember I mentioned that elements that are in row 3 or below can have expanded octets. They're going to make hybrid orbitals too, and they're actually going to make more than 4 hybrid orbitals. Where are the additional atomic orbitals going to come from? What are they? Well, it's going to be the d orbitals. The d orbitals are going to be used. They're going to be found in the same energy level as the s and p. Now let's take an example. Suppose our total number of sets of electrons is 5. That would be then an element from row 3 or below. The number of hybrid orbitals, of course, the rule applies, is 5. This means it's going to have to use 5 atomic orbitals to make those 5 hybrid orbitals. What are they? It always starts with the s orbital. All right, it's going to have to use all the p orbitals. You've got to get a total of 5 now, so it's going to take 1s and 3p. Well, to get a total of 5, how many d orbitals? Just 1. 1s, 3p, 1d gives a total of 1, 3, and 1 make 5. 5 atomic orbitals combining to make 5 hybrid orbitals. Now, this is really important. We know the number and the type of atomic orbitals that that particular element would be combining. It tells us the tag, the label, the type of hybrid orbital. That type of hybrid orbital is called an sp3d. Should be d1. That's a mistake also. Sorry about that. This should be sp3d. Oh goodness. S should be sp3d, not d2. All right. And I can see I got 6 here. This is not s. It's supposed to be 6. What are they? That we're going to need 6 atomic orbitals. What are they? Well, it's 1s, 3p, 2 ds. That's a total of 6. So, and this is correct. The type of hybrid orbitals would then be s, 1s, p3, 3p, d2, the 2 ds. Sorry, folks, for those errors on that chart. This just explains a little bit more detail about central atoms that make more than 4 hybrid orbitals, 5 or 6. This we saw this molecule before. This is phosphorus pentachloride. This is the correct geometry for it. That's something I'm going to discuss a bit later, how you predict the correct geometry for it. It's called, by the way, a trigonal bipyramid. The 3 chlorines are in a triangular plane. These 2 chlorines are on a vertical vertical axis through the p atom. All right. Well, there are 5 sets of electrons in this molecule, 5 bonds. You're going to need 5 hybrid orbitals. All right. 5 hybrid orbitals come by combining the 3s, the 3p, and 1 of the d. The d comes from the 3d sublevel. So it merges the s, p, and d orbitals here, total of 5 hybrid orbitals. There are 5 valence orbitals. They distribute themselves in each of the now created hybrid orbitals. What are they called? Well, 1s, 3p, 1d, they're called sp3d hybrid orbitals. And that's the nature of the hybrid orbitals. We could say the phosphorus is sp3d hybridized. All right. Now, resonance structures. Ooh, you've heard of that. We talk about that in organic chemistry. Here's a central question: can Lewis structures, Lewis structural formulas, always correctly and adequately describe the structures of all molecules? Well, the answer is going to be no. There's going to be a breakdown. Let's see. Here are three examples of molecules. This is a structure of a water molecule. This is ethene, and this is nitrogen. These structures you can get by applying the steps that we showed previously. These predicted or drawn structure formulas, in fact, experimentally agree with the structure formulas observed for these molecules, water, ethene, and nitrogen. Let's take a different compound though, sulfur dioxide, SO2. If you go through the steps of drawing applying the steps and drawing the Lewis structure, you come up with this for SO2. Central atom sulfur, double bond, and a single bond. All right, this is now what you get when you apply the steps. The question is, does this predicted structure correspond to the actual sulfur dioxide molecule that we observe? Well, this drawn Lewis structure for SO2 shows a molecule with one double bond, one SO double bond, and one SO single bond. Remember from organic chem that double bonds are always shorter than single bonds. Our structure here, our drawn structure, shows a double and a single bond. That would predict that in SO2 that there is a short SO bond and a longer SO bond. It predicts that we should see two different bond lengths in SO2. When we examine SO2 experimentally, this is through using methods of spectroscopy that can measure, determine the actual geometry, the bond lengths and bond angles. We get a big oops. Here's a problem here. The observed SO bonds in the actual SO2 molecule we don't see two different length bonds. We don't see a short and long bond. We see two bonds that are equal in length. The observed structure of SO2, I don't want to look at this, it's wrong, but the observed structure shows two SO bonds. They're both equal. Moreover, their length is halfway between what we see for a SO single and an SO double bond. The observed SO bond lengths lie midway between what we observe for an SO single bond, 170 picometers, and for a SO double bond, 143 picometers. Well, how can we explain the observed SO2 structure? And if our drawing failed to correctly predict the structure, well, what can we do to hopefully fix that? The approach that is used, and this is arose from people in the valence bond model school of thought, is you do this. To correctly draw the structure for sulfur dioxide, you don't just draw one structure. Well, you draw more than one. In this case, we're going to draw two structures. And those two structures differ in the position of electrons. You can take a starting structure, which, will correspond to our incorrectly drawn one, and then you modify it. You shift electrons in that structure to come up with an alternate structure. Both of them should be valid Lewis structures, not violating rules. So you're going to have two structural drawings. The understanding is that the actual SO2 is neither one of them, but an average of the two. So you're on paper, you're drawing two, or sometimes more, structural formulas. The understanding is that the real structure is neither of those drawn structures. The real structure is the average of those structures that you draw. Chemists call those drawn structures resonance structures. I don't like the name of that because it implies something that's really not the case. They're called resonance structures. That implies to one that you have a case where two molecules are resonating. Well, that's not the case at all. It's a bad term in that respect. The English use the term mesomeric structure. Anyway, we're going to live with that. They're called resonance structures. And the idea then is that a way to correctly show the structure of a molecule, you don't just draw one structure, you draw two or more, and they differ in the location of electrons. You can start with one, shift electrons to get the other one. Typically what we do is the two drawn structures are enclosed in brackets. They're separated by a double-headed arrow. That's a convention for telling us that these aren't real molecules here, they're just hand-drawn structures. The real molecule, real SO2 molecule, is an average of those. Now, let's see, in fact, if the idea behind this really works. You know that the real structure of SO2, both SO bonds are equal in length, and their length is about halfway between the length of a single and double SO bond. Well, the idea then is that the actual SO bond in the real molecule is the average of the bond we see in the first structure and the second structure. And for instance, let's do this. In structure 1, the bond between the sulfur and oxygen 1 here is a double bond, is bond order 2. In our second resonance structure, Roman numeral 2, the bond between oxygen 1 and sulfur is now seen to be a single bond. That would be bond order 1. Well, the average of bond order 1 and bond order 2, we weight them equally, that's 2 plus 1, that's 3 divided by 2 is 1.5. In other words, the average bond order that we're computing for structures 1 and 2 is 1.5. And they both would be, in fact, 1.5. That's showing us that the bond orders in the real molecule is going to be the same. They're both equal, 1.5. And the 1.5 would also indicate that the bond length is halfway between single and double. Now, behind all this there's an important implication that I need to point out. When you can draw two or more resonance structures for an actual molecule, the implication is that actual molecule, that its electrons are actually delocalized over the entire molecule. And so writing resonance structures, we're discovering, in fact, that real molecules, the electrons aren't just riveted, localized on atoms or between atoms. They're really delocalized over two or more adjacent bonds. And this as well, something we stress in organic is that this idea of spreading electrons out, delocalizing electrons, is something that imparts stability to the species. So molecules where you have to draw two or more resonance structures actually will then necessarily have their electrons delocalized, and that's going to help the molecule. It's going to make the molecule more stable. So this SO2 molecule, where we draw two resonance structures, is a molecule that has delocalized electrons. It's more stable than you otherwise expect it to be. And if you're SO2, hey, that's a good thing. All right, that basically completes the video. Thank you for watching. Let me know if you have any questions. Goodbye.